we started talking about pipelines. So pipelines are a pattern for concurrent data processing. You have multiple independent stages where data flows in the first stage and then flows through. It's useful for web servers, message processors, where you want to do stuff in parallel, asynchronously. It can make concurrency easy to work with, so that you can avoid threads, mutex locks, and such. And it still provides a lot of control over performance and resource use. So last time we talked about the stuff that's built into Go to help with building pipelines and concurrent programs. We talked about Goroutines and Channels and Select. Goroutines are functions that can execute independently of each other without blocking the caller. Channels are ways that Goroutines can communicate and synchronize with each other. And Select is a statement that enables multiple communication operations to happen at the same time. So we talked about those last time, so this time we're actually going to talk a bit more about the patterns that we use for pipelines anyways. We use pipelines pretty extensively on my team. I think I said, like, the last time I started making a program that didn't have pipelines in it, by the end it did have pipelines. So they're useful for everything. So this is the program we ended up with last time. So this is just using basic Go stuff. Well, all of it really just uses basic Go stuff. But, so this has kind of the elements we're going to build on this time. So this is basically a Go routine that returns an output channel, and it generates quotes and outputs those on the output channel every sort of random number of milliseconds between roughly 0 and 1,000. So we start out by there's also a wait group in here, so we pass in a pointer to a wait group so that we can control exiting the program. And we can make sure that everything is shut down nicely before we exit, so we pass in a wait group for that. We pass in a quit channel so that we can essentially close it or send a message on it when we want it to shut down gracefully. You can see we make the output channel, and then we have a loop that basically continuously outputs on that channel and then goes to sleep, and then we return the output channel. The other thing, and you can see that we have a select in the middle there where it allows us to basically output in parallel with checking for the quit signal, so that we can handle those sort of independently. So this is kind of what we're going to build on and turn into sort of, or have it follow sort of the pipeline pattern that I'm proposing. Yeah, I guess continuing on, this is the main routine that uses that quoter function. So we make the quit channel, we make the wait group, we set up 2 quoters, let them run for 5 seconds, and then while they're running, we're basically reading from the output channels and printing it to the screen, and then when the timeout expires, we stop, and then we close the quit channel and then wait for everything to shut down. This is the stuff that this is what we ended up with last time after multiple steps. So in this example right now, we're basically generating quotes and then we're printing them out. So you can kind of imagine turning this into a 2-stage pipeline where the first stage generates the quotes, and then the second stage consumes them and prints them. So the quoter has a single output channel, the printer has a single input channel, and that's pretty boring, but we'll add another stage later. So the things that we want pipelines to do, so we want them to shut down cleanly, either on demand, or if one of the stages encounters a fatal error, we want them to behave predictably. So normally if you're running a service that can run forever, maybe you don't care about being able to shut it down nicely on demand, but certainly if you're running like an integration test or something, you want to be able to start your program and have it stop and do things deterministically so that you end up with the same behavior each time. Generally, when we shut down on demand, we want messages that are already in the pipeline to finish processing, and if a fatal error occurs, though, all bets are off. We can basically drop the messages on the floor that are in the pipeline. We also want the stages to be easy to unit test, but you kind of get that for free. I guess you get some advantage in having consistent, interfaces to the stages, so you can build up. It's practical to build up some tooling around making the unit tests easier to work with. So conventions that we're going to follow are each stage is a generator that returns its output channel. The stages accept the input channel as a parameter, and the reason for this is just to have to know who's owning the channel and who's responsible for closing it. Because we want things to behave deterministically, so we are going to close the channels, and also use that as a signal. So stages stop processing when the input channel is closed. Stages are also responsible for closing their output channel when they exit, which of course triggers the next stage to close. We prefer passing the same message type between stages just to make things simpler and have the stages be more interchangeable. And of course the challenges we want to solve, which we kind of solved already in the program that I just showed, is we talked about how closing the output channel will trigger the next stage to stop. But what if one of the downstream stages has an error? How do we stop the upstream stages from trying to continue to write to their channels? Similarly, how do we avoid that upstream stage from blocking if the next stage has stopped? So these are things that we have to address. And feel free to interrupt and ask questions if you want. So one of the standard library packages that is useful is the context library. Not that it necessarily does that much, but it does some stuff that is worthwhile not to reinvent. So the context type carries deadlines, cancellation signals, and other values that are typically scoped to a request. So like an HTTP request, for example, or maybe a message coming in from a message queue. And usually the idea is that, because this is part of the standard library, typically you could pass that across API boundaries and have the context live as long as the request is alive. In this case, we're kind of just using a small part of it. We're using the cancellation signal functionality, and we're not really using it on a per request or per message basis. We're using it to trigger shutting down the whole pipeline. So not exactly as it's intended, but it kind of works.
I have a question.
Yes.
So deadline is not a particular case of cancellation?
Well, cancellation is like where you have an error occur and the code cancels the request. Or a deadline is like a timer that would expire. Mm-hmm. So they're a little bit different. I think you'd end up with the same result probably, but one of them is like time-based. So this shows how we would create a context with a cancellation signal. So we call context with cancel. Context.background is sort of the root parent context, if you will. So we get back the context as well as the done function. So when we want to trigger cancellation, we should call that done function. And then if we want, we can wait until the context is canceled by waiting on the done channel. And then in this case, I'm printing out a message when it's done. You can also define child contexts that are also canceled when the parent is canceled. So in this case, you pass the parent in as a parameter to with cancel, and the rest basically behaves the same. So in this case, because we call the done function on the parent, we would expect the child done channel to already have closed. So
another question out of curiosity.
Yeah.
I don't know if you're familiar with JavaScript, like promises and observables.
Yeah.
How this kind of brings similarity with observables, or?
No,
I guess.
This is more like the context pass-through on ASP.NET, like Web API. So when you have a cancellation token, it's more like that. In this instance, it is.
But from what I know in JavaScript, the reason for observable is to be able to cancel
Right.
a feature promise. Yeah, with the promises you cannot do that. So
Right. Yeah, I haven't gotten into some of the more detailed libraries and stuff. There could be similar things in Go, but it's not really part of the core language anyways.
the reason I'm saying is I've seen some videos when even a guy had a presentation where he says that he can replace all the like observable and reactive extensions that JavaScript now implements with kind of concept like Go channels.
Right.
Yeah. So
Yeah. I mean, you can do
like
similar things for
communication sequence processes. Yeah, where
Yeah.
it's more clean and easier.
Yeah. So, because we want sort of a few more functions, we typically sort of create a derived context type that also stores the done function and also has a wait group associated with it to allow us to wait for pipeline stages to shut down after the pipeline is canceled. So, and then we have a function that instantiates one. It does the stuff that we saw in the previous slide. And then I threw in a few helper methods to basically easily access the done channel. Another one to basically wait for the pipeline to shut down, and then lastly one that calls the done function and then waits for the pipeline to shut down.
So would code like that wait forever if the pipeline didn't shut down for some reason?
Yep, that it would.
So you could put a timer out or something on that if you wanted to, say it doesn't shut down after 5 seconds.
You could, but then you'd probably be just like concealing some other problem that
It's
shouldn't
obviously
happen.
a problem that's happening at all.
Yeah,
but-
it would be. And yeah, it'd be good to.
But nice not to see the machine just hang there.
No,
Get
that's
a
true.
Message and say timeout on waiting for pipeline.
But if it's gonna hang, it's better for it to hang like every time.
What do you mean by hanging? Like there's no input going into the channel, or like the channel is not?
Well, in this case, with a wait group, like if you have a wait group that hasn't decremented to 0 and you're just waiting for it to decrement, so it'd be because of a bug, likely. Oh, really? Yeah. I'm not that patient.
Yeah, it may depend on environment.
Yeah.
But yes. In some cases, it depends on what it's doing that's wrong. I'm not sure the wait group is sufficient of waiting the channel.
So now that we have this context helper, so we know we're going to be passing this into each of the stages. So we're calling wait, I skipped over something. Yeah, I skipped over this. So this run helper method, basically, we're passing in a function that we want to run as part of the stage. And we're incrementing the wait group counter, and then we launch the Go routine, and basically with that defer call, we're basically decrementing the wait group again when the Go routine exits. And then if our function returns false, we assume there's an error and we cancel the context. So the idea here is that the function returns true or false. If it returns true, we assume it's a non-fatal sort of termination, but if it returns false, then we're going to tear everything down. So then, so I've modified the quoter function here to use that run method, and you can see we're closing the output channel on exit, and we're also handling the done channel now. So the case where we're shutting down. So the print. So this is now this is the functionality that we used to handle in main. So now we have a printer stage. So the printer stage is basically going to now use the range operator to iterate over input messages. And the nice thing about the range operator, as I mentioned last time, is that if the channel closes, it basically exits the for loop. So it's kind of just syntactically nice to read. So in this case, we're basically iterating over the messages on the input channel until the channel closes, and we're just printing them out. So the main routine now creates the context, passes it in, and we have the quoter stage, and then we pass the output of the quoter stage into the printer stage, and then we're sleeping for 5 seconds, and then stopping. I'll start running these when they get more interesting, but you can just believe me for now.
Trust you.
Trust me, that's right. So slightly better. So something we had before is that we also want to have a way to shut down the pipeline normally, because it's kind of good to have the abnormal termination case separate from the normal shutdown case. And in this case, we also can make sure that the messages in the pipeline are fully processed, which is good. So because basically we're sort of cascadingly shutting down each stage of the pipeline as the last message travels through. So in this case, we're making an input channel and we're passing it into the quoter. And the input channel is just, it doesn't actually have a type. I mean, it has an empty struct, so which means you can't actually send a message on it. You can only close it. So that's handy if you want to make it like super clear that you don't intend to send messages on it. So it's just a signal that we trigger by closing the channel. Yeah, so in this case, we're closing the input channel and then we're waiting. Another thing we can add for fun, so as I said before, if we return false inside that run method, we do kind of an abnormal shutdown. So in this case, just for fun, we're going to say if a message is longer than 200 characters, we're going to abort. As you can see, if I run this now, it'll eventually. These are just like programming quotes. Some of them are a little off color. I apologize in advance. Yeah, so you can see we hit message that was too long and it aborted and everything shut down nicely as we expect. Yeah, you can go home and run it for an hour until you get offended.
No, I saw what I did.
Yes.
Yeah, that was fine.
Yeah, so another thing that's case is nice to handle separately is the case where we have like a bad input message. So in that case, we may want the input message to continue to flow through the pipeline, but we want to flag the message as having an error. And in that case, it's non-fatal, so we don't want to tear the whole thing down. We just want to basically identify the message as having some problem. And especially in cases where you have a final block, a final stage that's maybe sending a response back to in that case, you definitely want the error to pass through, so you're not having to like handle that kind of logic like at every stage in the pipeline. So at this point, I'm going to introduce like a common message type. So it has the quote string in it, but it also has an error instance in it that we can set if an error occurs somewhere in the pipeline relating to that message. And at this point, I'm also adding a send method that takes care of the case where the context has been canceled. So that's useful in the case where some downstream stages may have shut down. In that case, we know we don't want to send to the output channel. So this prevents that from blocking.
So if one stage detects and sets the error code, then the next stages might write over the same error code?
If you didn't have logic to handle that, yes, but you'll see I have like a helper function that will make that a bit nicer, which is this. So at this point, things have gotten complicated enough that it seems like it's useful to have a helper function to iterate over the messages. And it's also useful to have like a few options depending on the type of stage that you're running. So this function is going to iterate over the messages, kind of like I was showing before. In most cases, you don't want the stage to even see the failing messages. You just want to pass them through to the next stage of the pipeline. However, if you have if you have the final stage that actually is supposed to handle the errors, then you maybe would want to set a flag to say that we want to process the failing messages. So you can see the logic here. If there's no error, or we've said that we want the stage to process the failing messages, then we call the function and pass the message in. In some cases, we don't want to automatically, the other thing that this helper is doing is it's actually going to send the message for us when we finish processing it. In some cases, you may not want to do that, so it can continue and move on to handling the next message. If there's an error in the function and it returns false, we want to return false from here, so we can pass that back out and cause an abnormal fatal error. And then we just print out a message if we're actually skipping the block because of a past error. So this is just sort of boilerplate stuff that we don't really want to have to do in every single stage. So now the printer routine kind of looks like this. So we set up the options. I kind of prefer to throw the bools into a struct like this so that you can actually indicate the field names rather than just passing bools into a function, in which case you have to look at the function signature in order to know what they mean. So in this case, this is the final stage, and we want to display the errors. So we want to process the failing messages, and we also don't want to send the messages automatically out of here because we don't actually have an output channel because this is the last stage. So you can see here we're now checking whether the message has the error set. If it doesn't, we print the message out normally. If it does, then we print a special message saying that an error occurred. So it seems like there are a lot of different cases we're handling here, and at first we tried to avoid some of them and assume they were the same, but by the end we actually discovered that they all did have value when we actually started really testing this stuff. The other case that you may not think of right away, but we eventually found was useful, is being able to support test messages. So these messages just flow through the stages, and this is actually good and kind of necessary if you want to ensure that none of the stages have deadlocked for some reason. Because there's otherwise not really any good way to tell, except by maybe detecting that the real messages aren't working. But if you want to have a way of sending a test message through that, of course, is literally just being passed without actually having any processing done to it, then this is a useful thing to have. It also has a side effect that it can also show you the latency through the pipeline as well, in case you're curious about that. So this is a nice thing to have there, and to maybe wire up to a service health check or something like that, to make sure that nothing, as I said, that nothing is deadlocked. So in this case, I added just a simple test function that says that it's a test message if the quote has zero length. Oops. As you can see there. So basically, we can handle this entirely within that iterate messages helper function. So we're now if we have a test message, we're not going to pass it into the stages function, and we're going to print out a message just saying that we're passing the test message onto the next block, just for test purposes, or to show that it's actually working. So now this does complicate our first stage of it, because now with the test messages, we do actually want to have an input to the first stage and an output from the last stage, because that's where we're going to pass the test message into the first stage and then get the test message back out at the end. So essentially, that first stage that's generating the quotes on the timer, we basically want to adapt that so that if we get a message in on its input, a test message on its input channel, we pass it through to the output But we also need to handle the case where we close the input channel, because that was our sort of normal shutdown case. So we need to handle the case where either we're receiving a test message or we're shutting down that input channel. Does that make sense? Cool. So it's getting a little more complicated. So then in the last stage, there's not much that we need to do to handle outputting the test message from the last stage, except that we now need an output channel. So now it looks more like other types of blocks, or other types of stages rather. And then back to the main routine, we basically, rather than just calling it an input channel, I now call it a test input channel, then we have a test output channel. And we're passing the test into the quoter and getting the test out of the printer stage. And just to show how this all works, instead of shutting down after sleeping, we now send a test message. And again, for test purposes, I threw in basically handling all the different things that could happen that would befall our test message. So we create basically an empty message, which is sort of by definition that ends up being a zero object with having a quote of zero length in it. So that's our test message. So we're sending that test message in, and then there are a number of things that can happen. So we can try to receive the output message from test out, and we can find that the channel has closed, in which case we print out that the pipeline is shut down and the test failed. If the channel is still open, then the test passed. We can have the case where the context has been canceled, so we print out that the test failed because the pipeline canceled. And in this case, it's also good to have a timeout, because if you're deadlocked, then the thing will time out. So in that case, we can say that the test failed because the test timed out. So there are a number of interesting things that might happen. So if I run this now. Yeah, so in this case, the test message passed through, and then everything shut down nicely. So let's add another stage, because a two-stage pipeline is boring. So I added a filter stage that's calling a web API that basically, very poorly actually, identifies inappropriate language in the quote, and basically returns us a flag indicating whether the message is good or bad. So if it's bad, we're going to set the last error to. We're going to create an error and set that into the last error field. Of course, if the web API returns some other kind of error, we want to consider that to be a catastrophic failure, like a fatal error. So we return false, and otherwise we return true and send the message on. So because I said this stuff is testable, I just threw a quick unit test around this. So the actual tests are here at the bottom, and I just made a helper function that basically allows you to pass in a message and indicate whether you expect it to be true or false. For fun, I considered the word Perl to be a bad word, so I have that fail. So you can see that the actual test helper function looks a lot like the main routine. It's creating the pipeline, just the one stage in it, and then we pass in the quote that we're testing, get the output, and then check whether we got an error or not as we expected. And this is just using the built-in Go testing framework, which is kind of awful. So another interesting thing you can do with pipelines is it's relatively easy to do like a fan out, fan in type thing. So what if one of the stages is a bottleneck? It's either CPU intensive or tends to block for a while on like a long API call or something like that. In that case, it's pretty straightforward to have multiple instances of that stage. So in this case, we have multiple instances. So you can imagine we have, in this case, we're going to take the filter stage and have multiple instances of that. So it's relatively easy to have those multiple instances share the same input channel, because basically they'll just, when they're ready, they'll grab the next message off the channel, or they'll block until another message is there. So that's relatively straightforward. The more complicated part is what to do about merging the output channels back together, so the fan-in case. And the challenge there is just that you don't want it to be ambiguous who owns the output channel and who's responsible for closing it. So in this case, it's good to have like a special stage that just merges channels together. So this is actually taken from one of the Go articles on pipelines. So they have a stage just like this. So basically in this case, what we have is we're passing in our context, and we're passing in multiple input channels, and then we're merging those into one output channel. So it's reasonably straightforward. Basically what we're doing is using a wait group to keep track of how many of the input channels are still open. And we use the range operator to iterate over the messages coming on into each channel. And then when the channel closes, we're basically decrementing the wait group. And then at the end, we have a separate go routine that's basically waiting for all of the inputs to close. And then once all the inputs are closed, we close the output. So then, if we want to use this, the main routine actually doesn't change that much. So we have a constant defining the number of filters we want. So we have to make our slice of channels, of input channels. No, output channels, that's right. So we're making a slice of output channels. We're creating the multiple instances of the filter stage, and then we're merging those outputs together and then passing those into the printer stage. So it's really kind of quite like an isolated change to actually do this, which is nice.
Instead of doing a merge stage, is it possible to just take a list, like a slice of input channels, and then select on them? Is that possible?
You could. You'd have to know exactly how many. You can't really do that with a slice. You'd have to. Right. The channels have to be known.
So I have a question. So these filters are like a stream of messages?
Yeah. Basically each one of the stages is handling a stream of messages, and then you're just connecting them together like Lego. And so this doesn't actually look any different when I run it. You can't really tell that, except people see that 5 filter stages are shutting down at the end. Yeah, you can see it slowly tearing itself down. Oh, look, we got some inappropriate quotes. They're probably about Perl. So I don't actually have an example for this. So I guess the next example kind of incorporates this. So if you want to persist some data, and you don't need special synchronization as long as only a single Go routine is using it. So if you go and like declare some variables in one of the stages, I'll show you later. Basically, if you go and declare some variables in a stage before you launch the Go routine, you can basically access those as much as you want, because only the single Go routine would see those. The only case where you need to deal with synchronization is if multiple stages are sharing data. And usually you can avoid that by designing the pipeline appropriately, or at least we try to.
It's the Go proverb of don't communicate by sharing memory, but share memory by communicating.
Mm-hmm. The only problem is when you start getting into like cycles in the pipeline, things get a little bit complicated, which I'm going to show now. So one of the things you definitely want to do is avoid deadlock, and a good way to have deadlock occur is to have a cycle in the pipeline. So have like some output feedback into one of the earlier stages. You can still do that, but you just have to be careful about it. So I'm going to show an example where that can happen. So to avoid it, basically the solution is to make sure that your Goroutines are always able to service the inputs and outputs if you're dealing with a feedback situation, which I'll show you. So here's the deadlock examples. This is a totally different example now, not building on top of the last one. So we have a message in it now that has an ID field, and it still has the last error in it. So we basically have a subscribe stage, a bunch of processing stages, and then we have a respond stage, which basically is responding to the original requester. The interesting challenge here is that the subscribe stage is responsible both for getting the incoming messages, but also handling the response. So maybe it's using some API that the same connection is used to receive the request and send the response back, which is pretty normal. So in this case, just to make this simple, I just have a timer. So every millisecond, we're going to output a request onto the output. And you can see, so here we're actually returning 2 channels. We're returning the output channel, and then we're also returning the response channel, which is an input channel. So it's a little bit complicated. And so I'm going with the kind of naive approach right now. So we're going to basically, inside the for loop, we have a select that is waiting for the ticker to tick, in which case we send an output message with the next ID in it. We're waiting for maybe the context to shut down, in which case we abort. And we're also dealing with our input channel for the test messages, and we're also listening for our messages coming in on the response channel. And we also handle the case nicely, like if the response channel closes, we shut down, which is nice. So this seems like there shouldn't be any problem. We have select, we're handling all the inputs, everything's good. Unfortunately, we'll soon see that it's not good. So the response stage, I'll just finish going through this. So in the response stage, we're passing in the response channel. And in this case, we're kind of the response stage is taking ownership over the response channel. So it's going to shut it down. So that's all good, it's clear. And you can see here, basically, just to keep it simple, we're basically taking each message and sending it back on the response channel. Cool. And then the main function, so we've got our subscribe, we're getting our response channel back, we're doing a bunch of processing steps in serial here, and then we're passing in the response, and we're creating a response stage with the response channel. So this is all great. I didn't want to, it's pretty fast, so I just let it run for a short amount of time. So you can see we got our 100 messages. We actually send a test message at the end, and it's flowing through the pipeline. And then everything shuts down, and we think that everything's great. But we're wrong. So what happens if we decide to make things go a lot faster? So now we're deadlocking. So we get through sending the test message, and we deadlock. And the reason for that is because basically, I'll show you. So basically, the fast messages essentially fill up the pipeline, and so because we have this cycle in there, if we fill up the pipeline, we essentially have a case where we're trying to, from the subscribe stage, we're trying to publish a new message, but the next stage is busy, and each subsequent stage is also busy. And that's happening. So going back to the subscribe, can anybody tell where the deadlock is happening? So the problem is that basically as soon as we hit this line, we're trying to output the message, but we actually have a message coming in on the response channel at exactly the same time, and we're not in a position to handle it. So the solution to that is to basically turn that case that turn that output into another select inside the original select, where we handle the context cancel case as well as the response channel case. So basically, we need to always be able to handle messages coming in on the response channel as we're either receiving other messages or as we're sending messages out. Otherwise, the deadlock can fill up, or the pipeline can fill up. But actually, so this is actually good. So this is the same timing, but now it actually sort of works, although we're not actually shutting down properly. So there is another problem. So the other problem with our deadlock on the shutdown is that when the input channel closes, we still have to service the response channel until it closes. So this is basically a challenge with handling multiple inputs at the same time, is you don't know what order they're going to close in. And when one closes, you still need to continue to accept messages from the other one. So yeah, this is basically where it gets a little bit complicated. And yeah, we haven't found a really good solution for it other than to just add more code to handle these cases. Yeah, and as I said, the code does get a bit. So I'm showing the case where the input channel closes first, but then of course we have to handle the case where the response channel closes first as well. And yeah, things get a bit messy and repetitive in that case. But if you want things to work, that's necessary, unfortunately. And unfortunately, that's the end. So we're ending on the things get messy stage, which is great. That's how it goes. Any questions?
You can avoid most of that requirement by just carefully designing how your channels communicate. Like,
True.
If you're in that spot, you probably got another problem than just your channels being a little funky.
True. Yeah. Some things you can, if through design you can handle. Some things are just tougher. You may be using like an API that it's putting constraints on you that like you don't have complete control over.
What's the capacity of a channel?
Whatever you want.
Depends,
You know, if you have no reader, how much is it going to take before it
None.
stops taking any writing?
Zero.
Well, you write a string to it now, so it's got some capacity.
So basically, you have to have somebody has to be sitting there reading from it at the same time you write to it, or it blocks.
So the way the channels were done there,
Yeah.
when you see the make in the channel with no number after, that means it's essentially a single message channel. A single write into the channel without a read means the channel is full.
Yeah.
So it's not buffered. It takes one message.
If that message could be 20 bytes.
Yeah, oh, yeah.
There's
There's no
right.
inherent capacity. It's just the message size itself, right?
Yeah. The number of messages. So yeah, you can have buffered channels as well, but we don't tend to use them because unless you're literally buffering because you have an input that is coming at a variable rate or something like a I don't know, a TCP connection or something like that. In that case, you may want to have like a buffer, but in the cases where I'm showing here, a buffer channel is really just going to conceal problems.
It's kind of an interesting question because how many elements can a buffer channel possibly hold? Is it
Yeah, that's a good question. I'm not sure what the is. Anybody know? I don't know if it's a 32-bit int or 64.
More than you should.
Yeah.
More than you should. Yeah.
The headroom's there. You probably shouldn't use it.
Generally, 0 is the right answer.
So in your filter state, you basically ignore messages that kind of are inappropriate.
Yeah.
Would another way, would a possible way would be to decorate the message with maybe a level of rating, like a 13
Sure.
or something like that? And could you fork that off to different printers?
You
based
could.
on-
Yep. Yeah. So we do that as well. Like we have like a split stage that has multiple outputs and directs the message to one of those. Yeah, for sure. Yeah, you can do lots of neat like topology things like that. Then you can merge them all back together in the end if you want.
And are these all deployed as a single application, or is the entire pipeline a single application, or is every stage going to be a different application?
We tend to merge them all into one application. So with multiple pipelines running in parallel. Yeah, there's no reason you can't really do that.
So when you change as part of your deployment, when you change your running instance,
Yeah.
Basically it shuts down gracefully.
Yeah. Yeah, I mean, the shutting down gracefully is more useful when testing. As long as, I mean, it depends how durable your messages are as well, like how if you can allow it to just shut down or like.
Depends
Just
how
go on the side.
atomic the processing has to be as
Yeah.
well, where you want to avoid messages that were half processed.
Right,
In case
right.
there was writes to a database partway through something.
But yeah, in our case, like we handle like sync term and have things shut down properly.
So how fast is this processing? You have like a producer-consumer scenario. So let's say you can use this for like real-time stock trading. Yeah, they say you have like fast transactions. Yeah.
Yeah.
When the consumer have to keep up with the producer. So, but if the producer is very fast, then you lose some of the if you don't have capacity to buffer. So I don't know. Do you have any benchmark compare Go with C++, because C++ raves the speed? Yeah.
Yeah.
Gonna depend on how you process, really.
Yeah.
You can make anything take a long time if you want to. You can make it
True.
quick, right?
Yes, but that's my question. I mean, in the same scenario, C++ folks say that they are the fastest. Yeah, but yeah, just
They're
I
very
don't know.
close.
Do we have like test cases that
People have done test cases of different like real life applications, and it's really it kind of depends. It depends, like in terms of raw compute and CPU. I mean, yeah, you might be able to compile more efficient C++ code, but
Then you have to write C++.
but I like to. I mean, yeah. I mean, you also think about like, are you talking about like a very skilled C++ person and a very skilled Go person, or like a moderately skilled C++ person and a moderately skilled Go person? You could end up with different answers. But I like to think if your compiler is like super smart, giving it like higher level. I mean, like Go is a very simple language. So in theory, it has some interesting but it has a few interesting higher level constructs. So in theory, they can make a compiler that actually is really smart and emits very efficient code, which they pretty much have done. Like they've thought about, how to make code that can be compiled efficiently. And they basically left out the features that would make it inefficient. If there are no like templates, for example, which you can use to very easily like bloat your C++ code.
What it comes down to, because it's the simplicity and the writing of the idiomatic form of the language that's very simple and is what you see everywhere. It's actually easier to write something that runs fast in Go than it is to write it in something that may be faster in the end, because there is that large gap in between what you're experiencing in C++, I'm not as. So if we write something to do the same thing, you're going to do it a lot better than me. Whereas if we both write it in Go and we both follow the convention, we'll both be able to write something that goes very quickly. And that with each release, when they add more goodies to the compiler, they make it even faster just because you wrote it in the expected way, which is really nice. And the garbage collection in Go is silly too. Like, we're into microseconds now.
The things like if you were to make a properly like concurrent asynchronous program with channels and Go routines and such, and try to like implement the same thing in C++, it would be fairly challenging. And you might be inclined to like just slap mutexes on things, in which case you're likely going to end up with something that performs less well than the case with the Go routines and the channels. You could make something that works as well, but it'd be challenging.
This pattern is really good too for not in the multiple stages, in the single stage essentially of API clients or wrappers for an API where you make your client struct and then you make your API call methods, and each method essentially just contains a go routine and a channel it sends back, and allow the caller to decide how they block on it. And essentially the return is instant, and the caller can then wait to receive the response however they
That's kind of
want.
like a promise type.
Essentially, yeah. You can just send the channel back saying, I'm gonna send back and I'm gonna close.
Yeah.
Those are the two things I'm gonna do. And then if I close, or if I send you back an entity with an error in it, saying that there was an error on the response, you know what to do. But you get to decide how to block, and that's always I use that a lot. Very handy way. And it's simple. Like it just becomes the function of the language itself. It's right there to do. There's no adding it. It's just I make a channel, I do a go routine where I make the call, I send it on the channel, and then I return the channel in the synchronous bit. So all it is really just make the channel, return the channel, and then everything else happens in the background. And you have that sort of the nicety to it.
And in Go, you have a lot of control over, when memory, when you're passing things by reference or when you're copying things as well. So that's another potential case where you could be inefficient, but it tends to be fairly smart about it. It's also very clear if you follow conventions, like what's read-only and what's not read-only. So the compiler should be able to optimize that type of thing fairly well as well, without getting too complicated with, having to make sure that you declared everything appropriately. So
They do a lot
to
of-
do that in C++, you'd have to be, there are a number of conventions you'd have to follow to make things const correct and all that, to get the same level of compiler performance probably.
The work they've done with the compiler for the static analysis and the way they can inline things, and they've done a lot of really good work with it.
Yeah.
And that's one of their high points of focus too. They had some nice things to do, the general parts of the language, but they actually seem to do a lot of work in their compiler.
They wrote a lot of it in assembler and set it on the internet. C++ didn't do that for them.
You mentioned the Go built-in test framework. That's an execution framework? It's like a mocking framework that execute the tests?
There is a mocking framework as well, but the testing framework is basically it's a very lightweight, sort of almost convention thing. Like it expects you to have source files that that end with _test and functions that have certain names, and it basically just calls each of them. And then there's some other higher level libraries you can get to be able to, you can sort of do this with Go now as well, but organize tests into suites with like setup and tear down functionality. Similar to what you have with like Google Test or like NUnit or whatever with .NET.
The built-in is nice if you distribute your code, like if it's on GitHub or something, because no one needs anything. They can just get it, run the test, and they know as long as they have Go, if they can run it, they can run the tests without any problems. And you can do, it's pretty manual, but you can do most of your testing needs in there. You get most of it.
How much do you need to use like the benchmarking to help you to slice it into nice pieces?
What do you mean?
Like the Go test benchmark function.
I actually haven't used that yet. So, have you used it?
Just because
Yeah, haven't gotten to that yet.
It's pretty granular, and you can see the impact of different operations you're making. It's interesting because we were trying some base-62 to base-64 conversions. It somehow detects that base-64 is much faster based on some of the digit analysis. So
Cool.
quite a lot of interesting stuff.
Andy's been having fun with the new race detector.
Yeah, we might be talking about that at some point. But Go has a really nice command line option when you are building or testing or anything, dash race, and it will actually modify how it's handling Go routines in order to try to cause race conditions, and it will log those for you and tell you what lines exactly were accessing the same variable from different Go routines. So that the weight group example that we had there, I want to say that there was probably a race condition in that, just based on what I've seen in our code in the last couple of weeks. It's just cases like that where if you run 2 go routines, they probably aren't going to run in the order that you expected them to. And in some cases, they may be running much, much later than you expected them to, like 5 or 6 go routines behind sometimes. So it was, yeah, it's interesting.
That's the other thing that the Go developers also deliberately like randomize things in your program to force errors to occur. Like every time you iterate over a map, it randomizes the order, so that if you don't accidentally fall into a trap of thinking that things are going to happen in a certain order each time.
Blessing and a curse.
Yeah, but at least you know right away if you.
Well, that's the point of trying to force you into the idiomatic form of the language so that it's reproducible. Every result you get should be reproducible every time you do the same thing.
Yeah, in the case of the maps, I believe it did used to be the same every time, in every execution. And they randomized it on purpose because they wanted the option in the future to change their algorithm to something that may not be in the same order every time. So as long as you're not relying on undocumented stuff, then they're changing it.
Thank you, everyone. Have more pizza. Is there any left? So next time will be a percentage. Somebody to be determined will be presented, or all of you at the same time.
At least do it once a day.
Oh, but we got a bunch to figure out.